All right, there we go. Write the expression in standard form A plus BI. So they want me to take two complex. Hey, by the way, what is I?
Imaginary.
Square root of -1.
Yeah. I, does I actually stand for imaginary? Yeah. It's a square root of -1, right? That's correct. Why is the square root of -1 imaginary? Because it's not real, huh? Yeah, you can't do it, right? Right, because remember, square root, like take square root of 9 or something, it's 3, because, as you know, 3 times 3 is 9. So you can't do the square root of -1 or negative anything, because what times its very self would ever be negative? It can't be. You can't take -1 times -1, that'd be +1. You think, well, do one positive, one negative. Well, that's not times its very self. That's times the opposite, right? Square root asks what times its very self is this thing. Nothing times its very self ever comes out negative. A negative times itself is positive. So it's imaginary. Now, why, hold on a minute. Why are we doing imaginary mathematics? Thank you. It's all imaginary. I like that. I'm getting through at least to one person. Right? I never got this. I went pretty far in math science, and I went pretty far before I got this. I was in calculus and other stuff, and then it hit me. Oh, we're just making this up. Math is just being made up to do things that are real. I didn't realize how it all fit. So are you getting it all? Because a lot of times students will go, well, let's imagine. What's this crazy? What are we doing? And I want them to know it's all imaginary. All of math is imaginary, not just I. It's all made up, right? You can't taste, touch, or smell the number 3 even, right? There's no such thing. But we all know the concept of threeness, so we can talk about things that are real. If I saw 3 cars in a collision on Blackstone and McKinley, I'd come to class and say, I saw 3 cars, head-on collision, Blackstone and McKinley. You know threeness, I know threeness. We can talk about things that are real. But it's made up. There's no such thing you could grab hold of that's threeness, right? We've made it up. So all of math is made up. So now, do imaginary numbers then have real-life applications? Because math is made up to do things that are real. Are there real-life things done with imaginary numbers? Yeah, absolutely. Maybe our last 5 minutes, I was looking on Google just yesterday, and you can do that right now if you want. But yes, there's tons of real-life things that are done with imaginary numbers. They're made up for a purpose, to do things that are real, especially circuit design. Current, amperage in circuitry, in electronics, they use it all the time because it represents a secondary thing. Now, there's a complex number. We're in the world of complex numbers now. What is a complex number? Let me give you that before I give you the rules here. We're making up something new again. We made up vectors a minute ago, well, a day ago. And now we're making up complex numbers. What is a complex number? It's got a real part and an imaginary part. Real, 3, you can have 3 erasers in your pocket. And then imaginary, you can't have 4 erasers in your pocket. That's impossible. So if you put a real part and an imaginary part together, you make a new thing called a complex number. It's complex because it's not simple. It's got 2 parts to it. Real part, imaginary part put together. It's called a complex number. There's a whole world of complex numbers. They do all kinds of things with complex numbers. There's upper division math classes where you prove all kinds of properties about complex numbers and what they do and don't do and all that kind of stuff. We'll keep it simple. We're going to add, subtract, multiply, and divide these new things, and it's really very, very simple. It's a very easy section. So we're in a new world again, right? Just like vectors it's a whole new world. Just like vectors were a new world, now complex numbers are a new world, and whenever you're in a new world, you got to know the rules there. How do you add them, subtract them, multiply them, divide them? All right. But like I said, what it's useful for, what complex numbers are nice for in real life, is they represent 2 different things. Things in life which have 2 components to them, not just one, can be represented by complex numbers, and it's very useful. So amperage is one of the key things. Like coming out of the wall, that AC, the 120 AC coming out of the plugs in the walls right over there, that is a sine curve, actually. And so the phase of that, whether it's high or low, remember phase shift? The phase of that and the amount of amperage itself are represented by, the amperage is the real part, and the phase it's at, where it's at in its cycle, is represented by the imaginary part for people that do electronics work. They represent them with complex numbers. So the i's not really, they don't go, oh, this is imaginary. They're not thinking that. They're just thinking this is representing the phase, and this is representing the amperage. It's all just made up. They know that, but it's, well, maybe they don't. I don't know. But anyway, they're just using it to represent things. That's what they're doing. All right. So enough said for now. Let's get down to the rules. How do you add two complex numbers?
Add the reals and add the imaginaries to them separate.
Now we're making this up. Is that what you'd say you would make up? I mean, we're not making it up. We're trying to imitate what they made up. Yeah, is that how you would do it? Well, you guys have done this. You guys have done this in algebra, huh? I'm not really telling it to you for the first time. You're absolutely right. That's exactly right. You just add the 1 and the 3 is 4. You add the minus 8i and the plus 5i, it's minus 3a. It's just like terms. It's just exactly what you would expect. You remember this from algebra. I'm sure you guys have had this, right? Had some of it already? Totally simple. Right. All right. 3 here. All right. So 9i times 2 minus 2i. All right, so we want to multiply. So I just jumped over adding, subtracting. That's simple, right? Adding, subtracting complex numbers. Now let's multiply complex numbers. So how do we multiply these complex numbers? I'm going to go boom and a boom. So 9i times 2, 18i. No big deal. Remember from algebra? What about 9i times minus 2i? Minus 18i squared, right? Good so far? Now, does anybody remember? We do something special here.
8 squared equals
I squared equals
1.
what?
Right.
What is it?
-1.
Is it negative 1? I think so. Yeah, let me prove it to you. Do you guys remember what's the square root of 3 times the square root of 3?
3.
Square root of 9, which is plain 3, huh? Plain 3. What's root of 5 times the root of 5? Well, it's root of 25, which is plain 5. So what's the root of whatever you want to pick? 10 times the root of 10. It's root of 100, which is 10. Right, you get the idea. When you have two identical roots, it ends up just being one of those plain, doesn't it? Root 3, plain 3 in the end. Root 7, plain 7. Root 29, plain 29 in the end, right? We can just jump there. Root 29. It's going to be plain 20, right? Right? Okay, so what? Well, I squared is I times I. And what's I again? Square root of negative 1, right? So what's square root of negative 1 squared? We'll put it over here. What's square root of negative 1 squared root of negative 1? Negative 1. Isn't that the rule? Right? Two identical, one comes out. Right? Is that good? That makes sense? Now, I know you might be thinking, wait a minute, Sharon, wait. If you multiply those together, that's square root of 1, so that's just 1, not negative 1. You can't do that. It's the rule that says the square root of a times the square root of b is the square root of ab is not true for negatives. So anyway, long story short, I don't want to bore you with too many technical math facts. This is not true, though. That's why it's not 1. It is negative 1 is the truth. Two identical in, 1 out. It's negative 1. Okay, so what? Why am I saying all this? Well, that means whenever you see I squared, you remember this from your algebra days? Whenever you see I squared, you never leave it. You replace it with negative 1. Whereas I, we just leave as I. Because I is weird. I is the square root of negative 1. We don't want to do anything with that. But I squared is just a plain old real life number. Right? Isn't that weird? That I squared comes back into the real world? I is imaginary, but if you multiply two imaginary numbers, you get back into the real world. Isn't that strange? There's some interesting properties in the complex numbers. So I squared is actually a plain old. You can say, I lost 1 pencil yesterday. Right? I lost $1. I squared. It's a real life number, but you can't say I lost I pencils. That can't happen. So whenever we see I squared, we replace it with negative 1. We never leave I squared, but we leave I. So what do we have? 18i plus 18. There's the answer. So it really just reverses the sign of whoever it's with, huh? I squared does, because it's negative 1. Good? All right, so 3 minus 5i, 6 minus 7i. Let's multiply. So go ahead and multiply those together. Do the whole FOIL thing. Hey, I was a little firm on Monday, but I think it's for good. I really don't want people leaving 5 minutes early. I'm not trying to do that just for my ego or something, but it's not right because everybody else, because it distracts everybody. When everybody starts leaving 5 minutes early, it distracts, it wrecks the last 5 minutes of all the other people around you. And they have all paid money and given effort to be here and learn for the full time. So be considerate of those around you. I'm sorry if you made other commitments and stuff like that. That was not right of you. We've all committed to be here till the end, and it's disruptive for us to be leaving early like that, right? That's not kind to those around you. So please don't do that. All right, so go ahead and FOIL that out. And when you get to I squared, replace it with -1. Just everything else is normal. But when you get I squared, replace that with -1. So FOIL that out. 3 times 6 is 18. Minus 21i. We good so far? That 3 went to both. And then the minus 5i goes to both. Minus 30i plus 35, 2 negatives. Multiply to be positive. I squared. Good so far in that. All right, now combine like terms, and you know what you do with that I squared, right? You don't leave that I squared as it is, you change it. So 18, and then these two, is that minus 51i, combine like terms. And then what do we do? The 35i squared becomes -1. Like that. And then we have 18. I'm going real slow. You could skip some of these steps totally. So you could jump right from here to the -35, huh? The I squared term will always just reverse its sign. So 18 minus 35, what is that? I don't want to mess up again. 17 minus 17? Minus 17 minus 51i. So there it is. There's the complex number answer on that one. Is that good? We good there? Questions on that? Remember that from algebra? Subtracted, multiplied, and now, so we're already kind of at the end. We're dividing complex numbers. We've added, subtracted, multiplied, and now we're going to divide two complex numbers, right? That's dividing. I mean, the number on the top is just a real number, but same thing. We're dividing involving complex numbers. So how do you do that? How do you divide two complex numbers like that?
You multiply the conjugate.
Good. You remember all this stuff, Whitney. Did you work ahead? You remember all this from algebra? I'm impressed. Not many people remember this. Yeah, I bet my own algebra students might not remember all this. I'm teaching algebra right now and just doing this. Just did this like 2 weeks ago. Yeah, you multiply by the conjugate. Do you remember that? Multiply by the opposite sign in the middle of the bottom. So let me write this way. When I in denominator with a plus or minus. That's what we're talking about. When you got a plus or minus along with I in the denominator, multiply by what's called the conjugate. I'm not going to quiz you on the names. By the conjugate, which is opposite sign in the middle. So we're going to multiply by 4 plus I over 4 plus I, top and bottom like that. And we're going to run out of time. We're not going to finish this one. So I will